affected nearly all processors that have been deployed today on computers, on servers, on your phone, and the attacks are devastating, okay, in the sense that they allow an attacker to have complete and total control of your machine. And so my goal today is to tell you about these attacks. I might not get the time to tell you all about Spectre, but I will try to tell you everything about Meltdown. And the goal is not just to tell you about these attacks, but also to give you a sense of excitement of the kind of creativity that goes into computer security. Okay, so there is a lot of out of the box and creative thinking that goes into attacking systems. We are talking about attacks, and there is similar creativity involved in coming up with defenses. And the nice thing about these two attacks is that Meltdown at least has the beginnings of a defense. Nobody knows how to defend against Spectre, not till today, okay? So maybe one of you creative people in the audience will come up with a solution, okay? So let me try to infect you with the excitement of this field. Okay, so I'm going to actually delve into the technical details of Meltdown. If I have time, Spectre. And the goal is to try to explore what went wrong and to try to examine proposed defenses, at least for Meltdown. And I want to keep the talk informal, okay? So I don't want to cover a lot of stuff that all of you understand just superficially. I would much rather that we go slowly and you understand at least one thing in detail, okay? So please correct me if, many of you are active, you read forums and so on. If I say something wrong, feel free to correct me, okay? And if you have any questions, feel free to stop me, okay? And if you've heard anything about these attacks, feel free to interject and share your knowledge. Okay, so why are these attacks so dangerous? Well, one of the most dangerous forms of attacks is when an attacker is able to control arbitrary portions of your computer's memory. For example, read arbitrary contents of your computer's memory or write to arbitrary locations of your computer's memory. The reason is because if they can read arbitrary locations of your computer's memory, they can read, for example, passwords that are stored in memory or cryptographic keys that are stored in memory. Okay, and writing is even more dangerous because now they can get the computer to behave in any way that they want to. And what makes these attacks, Meltdown and Spectre, particularly dangerous or new is that they do not exploit any known vulnerabilities. Most computer security, most hacks that happen exploit some known bugs that happen in software. When you're writing programs, you end up making a programming bug. Some attacker comes and figures out a creative way to take over the program by exploiting that bug. The nice thing about these attacks is that they exploit features. There are no bugs, right? They are going to take existing hardware, which is correct, which has been proved correct, which has been selling for the last 20 to 30 years, and they take over the system by exploiting what are considered today features, okay? And as I was saying, there is only a defense that's been proposed for Meltdown. There is no defense that's been proposed for Spectre, and even the defense that's been proposed for Meltdown, there is quite a bit of controversy in the community. So this is a quote from Linus Torvalds on the patch that has been deployed for Linux to protect against Meltdown. It causes instability in the machines and it causes the machines to crash, right? And if you think about the business of computer security, the way it works is that there is some high-profile attack that makes it to the headlines today, and all of a sudden companies are scrambling to develop fixes. And what happens when you write code in a hurry? What happens when you try to submit your homework the night before the homework is due? More likely than not, you lose points, right? That's exactly what is happening, except with huge economic consequences, okay? So the thing is that these attacks are extremely spectacular. When you see them and when you understand them, they completely blow your mind. And the reason is because, how many of you have taken a course in computer architecture yet? What about operating systems? Okay, you would have learned everything that there is to know in order to exploit the system in your courses already. Chances are that you would have learned it. And all it took was some creativity to put these pieces together and come up with the attacks. Okay, so these attacks, Meltdown in particular, uses a trick called out-of-order execution, which is completely standard in all processors today. In fact, pipelining implements out-of-order execution, okay? And Spectre employs a more general form of speculative execution called branch prediction. All processors, they try to predict the outcome of branches, if then else branches, and then speculate forward and keep moving forward. so that they can try to speculatively execute your program. When the concrete input becomes available, they just concretize that state. So they don't actually have to spend cycles when the input becomes available. Every processor has implemented this since nearly 1985. Okay, it's almost unimaginable to think about switching off these features. No processor vendor will switch off out of order execution and branch prediction today. Every processor that's sold sort of bakes in these tricks in silicon. Okay, and they're completely standard and implemented by all modern processors. So, turning them off is not a defense. You can turn them off and these attacks won't work. No processor vendor is going to do that. Okay, so this is my first reaction when I saw this, and this you will too, right? So, in fact, the industry couldn't really believe that these attacks were possible, and this, essentially, their first reaction was, this cannot happen. This is a feature we have been using. How can this attack even happen? And the range of reactions, it went from disbelief, and speculative execution actually came out of the academic research community. And so there was post-mortem analysis of what could have gone wrong, and how do we fix hardware that is not really broken, right? If you have got correct software that is working according to the specification, that does not seem to have anything wrong according to the specification, what do you fix, right? I mean, how do you prevent these attacks? So there were post-mortem execution analyses, and this particular, you can see the headline there. This is from one of the pioneers of speculative execution. These are the people who actually developed speculative execution, out of order execution, and so on. And they made hay while the sun shines too, right? So they said, forget security concerns. Speculative execution has actually speeded up processors for 30 years. Okay, so this is sort of the make hay while the sun shines reaction. All right, so let's get into the technical details. I'll tell you a little bit about the kind of background that you need to know, the prep work that you need to know in order to set the foundation for the attack. And then we'll go over the meltdown attack in detail. So how many of you have read assembly code? Okay, good. So we will be looking at assembly code, because some of what you do in computer security is actually very low level thinking about what happens within the machine. And we will necessarily need to have to look into some assembly code. If you have not, don't worry, we will actually go over. It's just 5 instructions. It'll blow you. The meltdown attack is 5 assembly language instructions. Okay. So, all right. So let us look at the building blocks. The first building block that we need to understand is the notion of a process virtual address space. Every modern processor, when it starts up a process, it endows that process with a virtual address space. Okay, so on a 32-bit processor, the address space is 32 bits long, right? So 2 power 32 locations in memory, and on 64-bit processor, it's 2 power 64. And this is typically how the virtual address space is laid out on for a 32-bit machine. This is typically how it's laid out. The top 1 gigabyte of the address space is reserved for the operating system kernel. It's loaded into every processor's virtual address space. And in the bottom 3 gigabytes, you have things like the processor's code, which is in the text segment. You have the heap, where you get memory from if you use a malloc, and you have the stack right up on top, and you know that the stack and the heap go towards each other. Okay, so the process code is loaded and it's allocated into this address space, and every process's address space is logically isolated from every other process's address space. Okay, so one process cannot manufacture a pointer to another process's virtual address space. There is no way that one process can go and access the memory of another process except from within the kernel, right? So it can request the kernel to go and perform remote memory operations on another process, but that requires explicit authorization from both, okay? So you set up, for example, things like remote procedure calls and so on. That's completely different. But one process cannot manufacture a pointer to go and access another process's virtual address space. And this is a security property that's guaranteed by the operating system. So how does the operating system guarantee this? What is the data structure that it uses to manage the process virtual address space? The page table, right? The page table basically translates between virtual and physical addresses. So a process never gets to see the physical memory. It only sees an illusion of physical memory. Okay. So so I mentioned that the kernel is loaded into every process's address space, right? So one of the things that you want to ensure, so the kernel, of course, manages all processes on the system. The page tables for every process are loaded into the kernel. So the kernel is managing scheduling everything for all processes on the system. So how is it that the kernel is loaded into the process address space and you have a sense of isolation? How is this guaranteed, right? So if the kernel is loaded into the process address space, couldn't this process, for example, manufacture a pointer? It just creates a pointer to some location inside the kernel address space, look at the page table of another process, and follow pointers from there and look at the data in another process memory. So this should not be allowed, but apparently it is allowed if you look at this address space, because the kernel is loaded into the process virtual address space. So how is this isolation achieved? So on modern processors, the kernel is isolated from the processor by means of hardware. Okay, so the hardware, if this process were to ever to try to create a pointer that references the top 1 gigabyte of the process address space and dereference it, the hardware will immediately throw a fault. Okay, so the process isolates the kernel from the rest of userland, right? So everything in the bottom 3 gigabytes is called userland because it executes in user space, and the kernel is isolated by the hardware from the rest of userland. Okay, so every processor ensures this, and this is why if you want to actually go and access the services of the kernel, you have to make a transition from user space to kernel space. How do you make this transition? You make it using a system call. A system call logically changes the processor's execution mode from user mode into kernel mode. Okay, and that is what allows the process to step from user land to kernel land. Okay, so this is going to be an invariant that we would like to maintain, that the process should never be able to access kernel memory, which means read to or write from kernel memory, except by making this one transition through a system call. Okay, so the hardware will trigger an exception if the userland code tries to access kernel memory directly. And this you already know. I asked a question, you guys already answered. The OS manages the memory for all processes using page tables. Okay, and the page tables for every process are mapped into the kernel itself. So the kernel memory contains the page tables for all the processes that are running in the system. Okay, so in some sense, if you were to access the kernel, you have complete access to the virtual to physical mappings of every process that's running on the system. So it's very dangerous, for example, to get access to the page table, because then you will know which memory locations to go and access and then read the contents of other processes. Okay, so that's as far as the security property that we want to ensure. We want to isolate the kernel from the userland. So let's look at another building block, which is that of the memory hierarchy, right? And this is a picture that you would have presumably seen when you start learning about memory in computer architecture, right? And the memory hierarchy basically says that there are various forms of storage that are available on a machine that range from a very small quantity of storage that's extremely fast. This is in terms of registers that are implemented on the processor chip, followed by the L1 cache, the L2 cache, the L3 cache, then physical memory, which is DRAM, and then storage, okay, which might be SSDs, and then actual tape drives, disk drives and tape drives. Okay, so L1 and L2 are typically private to individual cores on a multi-core machine, and L3 is typically shared across all of the cores. Okay, so L3 is the last level cache. It's also called the LLC. So it's shared among all execution cores. And caches store objects in what are called cache lines. Okay, this is typically 64 bytes or so. That's the granularity at which you store things in the cache. So when you read data from physical memory, it's first brought into the L3 cache, then the L2, then the L1, and so on. Okay, so if something is there in the L1 cache, you know it's in the L2, in the L3, as well as in memory. Okay, that's the invariant that's provided by the memory controller. All right. So we have seen two building blocks so far: this notion of the process virtual address space, the notion of the memory hierarchy, and the third one is actually a security building block. Okay, and what I'm now going to show you is I'm going to take this notion of the memory hierarchy, the fact that, so if you look at this memory hierarchy, it's very fast to access registers. Okay, it takes on the order of a few processor cycles to go and access registers. a few more processor cycles to go and access the L1 cache, some more to access L2, some more to access L3, and once you go to physical memory, it's in the order of microseconds, okay? And of course, now once you hit disk, it's on the order of milliseconds. So there is a time difference that's involved in accessing data based upon where it sits in this memory hierarchy. So what I will now show you is an important tool called covert-channels. In particular, cache-based covert-channels that will allow two people to talk to each other without explicitly passing messages to each other, okay? So we've got two people here, and in the standard terminology of security, this is Alice, that is Bob, okay? Now, Alice and Bob want to talk to each other, okay? In the sense that Bob wants to pass a message to Alice, but Alice cannot directly talk to Bob for whatever reason, okay? So it's not like Bob can directly give the message to Alice. So what we are going to do is that now we are going to leverage the cache hierarchy to allow Bob to pass some data over to Alice. Remember, the cache is a piece of memory that is shared across all processor cores, in particular the L3 cache. Depending upon the processor the processes that are loaded, you know, the process virtual address space is private to every process, but the cache is actually shared. It's a piece of hardware that's sitting on the machine, okay? So player A in this case is now going to use the fact that if you access something in the cache, the access time is much faster than if you were to go and access it from memory, okay? They're going to leverage that one fact to let Bob communicate some data to Alice. In particular, we will ask in this case, we are going to think about everything in terms of communication of integers. Okay, so Bob has some integer in his mind, he wants to communicate it to Alice without passing the integer directly to Alice. So how would this proceed? Well, the first thing that Alice would do is that she would perform the setup for Bob to pass this message. She will use instructions that are available in the processor, in particular the CL flush instruction, to go and flush the cache. Okay, so what does this mean? Every line of the cache is now going to be cleared out and evicted to memory. Okay, so that's step one. The second step, what she's going to do is that she's going to create something called a probe array. And this term is going to appear over and over again in the talk, so keep it in mind. A probe array is nothing but an array of elements where every element is of a particular size. We will see what that size is. But she creates this probe array in memory. It's going to sit in memory. She can do this using a malloc call or whatever. She just creates an array of elements. And in this particular case, she's going to set it up so that every element of this array occupies one cache line. Okay, so it's very architecture specific. If you have a 64-byte cache line, every element over here is going to be 64 bytes long. Okay, so this is called a probe array, and she just creates it. Doesn't matter what the contents of this array are, she just creates it. Okay, so that is the setup. Alice has set up everything for Bob to communicate the secret to Alice. Now what Bob does is that he wants to communicate an integer x to Alice. All he does is that he goes and accesses the index x of this array, okay? The xth element of the array. So what happens when Bob accesses the xth element of the array? What would the memory hierarchy do? What would the memory controller do? Index out of bounds. Well, yes, sure, but over here, let's assume everything is within the bounds. What happens within the hardware when I go and access a piece of memory? Well, if it's not in the cache, it's going to bring it into the cache, right? So it's not in the cache in this case because Alice flushed the cache, okay? We know that the cache is empty. So the memory system, the memory controller is just going to go and bring that element into the cache. Doesn't matter what the contents of that location are. All that matters is the index to that location, okay? So the element is loaded into the cache. Now, so what is important to understand here is that in doing this, Alice still does not know the value of x, okay? So there is nothing in the architectural state of the machine that reflects the value of x to Alice. But what has happened is that the microarchitecture has changed. So what is the difference between these two terms, architecture and microarchitecture? What is architecture and what is microarchitecture? Looks like you have to go and read Hennessy Patterson again. So what is architecture? So architecture is what the programmer can see, okay? The instructions of the processor, the features of the processor that are exposed to the programmer. Now underneath the covers, the processor does a lot of things. Pipelining, it's not really exposed to the programmer. It's a trick that the processor implements. Caching. Strictly speaking, I can implement a functionally correct processor without caching. Right? Caching is a performance trick that's implemented under the covers. The programmer does not have to know about caching. Everybody, we study object-oriented programming, we study abstraction. Right? This is how complex systems are built. They are built using layers of abstraction. Tons of complexity is hidden under simple layers. Right? And this is also the way you have to structure software in the field. Abstraction, abstraction, abstraction. Okay? So microarchitecture is the complexity that sits under the architectural interface that is exposed to the programmer. So the microarchitectural state that changed over here was that the cache line got filled with the X element of this array. Okay. Now can you tell me how Alice will go and figure out which element, what's the value of this X that Bob is trying to access? Okay. So what Alice would do is that she would just have to write a program to iterate over the elements of the array, all of the elements of the array, and measure the time that it takes to access every element. Okay. What will happen? So it takes lesser time to access the X element. Every other element is going to take a longer time to access because it's being brought from main memory into the cache, but the X element is already there. Okay. So as far as Alice is concerned, and this is a real experiment that was done, you will see, if you plot the amount of time that it takes to access every element of this probe array, just the X element, you will see this dip. Okay, so this is a signal that you're seeing that tells you what the value of X is. Okay, so this is called a cache-based covert channel. It's a covert channel because Bob is not explicitly communicating anything to Alice. All they are doing over here is that they are leveraging the fact that the cache is shared. It's shared architectural state. It's a shared piece of hardware that stores some microarchitectural state that is then leveraged by Alice and Bob to communicate with each other. Okay, so this is actually a very important point because this shows you how hard it is to design real systems. We all think about, security properties when we study courses like cryptography. We look at, what we need to accomplish in terms of security. We design protocols, we design systems, but we stop there, right? We never think about the real world implications of taking a system and building it and looking at the security properties end to end. And we cannot, right? Who can have thought about such a side channel when they were initially designing the memory hierarchy, right? You brought this for performance. Without the cache, no processor can exist today because processors will be unbelievably slow. Okay, so but the cache is used as a side channel over here. Okay, this is a building block that we'll use. We are still in building blocks. Okay, so we are going to use this as a black box to implement our meltdown attack. Okay, so there are two terms that you'll often hear: side channels and covert channels. So the difference is that we are going to be using covert channels. The difference is that in a covert channel, the attacker is going to control both ends of the channel. Okay, whereas in a side channel, the victim is on one side and the attacker is on the other side. Okay, this is just a terminological thing, but if you've heard these terms, this is the difference. If you have not heard, you can ignore it. Okay, all right. So we are not yet done with building blocks. Let me tell you about the building block now for the meltdown attack. So what is out of order execution? You might have seen this in some form. You might not have seen it when you studied a course on computer architecture. But the idea is that in out of order execution, the processor, the hardware is allowed to execute instructions speculatively based upon what data is currently available. Okay. So let me show you an example. So let's take these three instructions over here. There are three instructions: an LW instruction, an add instruction, and a sub instruction. Doesn't matter exactly what these instructions do, but you see that there is a data dependence between this instruction and this instruction. You're loading this value into this register, which is then being used for the add. Okay, so in some sense, the add has to block till the load is completed. But the subtract instruction does not really depend upon the output of the load. So as far as the processor is concerned, it can feel free to reorder this, execute the subtract, and then wait for this load to complete because it takes several clock cycles for instructions to complete, and then perform the result of the add when the result of this $3 is loaded into that register. So this is called out of order execution. Processors routinely do this. They take instructions, they put them in something called a reorder buffer, and then they reorder the instructions, of course, subject to these data dependence constraints. and then execute them as and when the data becomes available. Okay, so this particular example that I showed you is something called dynamic scheduling. Okay, and there are also other tricks for speculative execution. We might see this if there is time. This thing called branch prediction, where you try to predict the outcome of a branch, whether the branch will go true or false, and then try to execute code based upon your prediction. Okay, and this is an instance of speculative execution. Okay, so the key thing to note is that the instructions execute speculatively out of order, but you don't actually see the result of these instructions in the sense that they are held in temporary state within the processor, but they are never committed into architectural state. Okay, so the fact that this subtract executed before the add, the result of the subtract will still not be visible for the programmer to consume, because if I execute the subtract before the add, it appears after the add in program order, and that illusion is not broken by the processor. Okay, so the processor is going to execute it, is going to store the result of this $5 somewhere in temporary storage within the processor chip, and then when the add is complete, it then just commits the value, right? Then committing just means that you don't actually have to perform the add, you just have to copy the results into programmer visible locations, such as registers. Okay, so what we say is that instructions are executed speculatively, but they're not committed until the program reaches and then executes those instructions in order. Okay, so when instructions complete execution and when the results of those instructions are available in architectural state for the programs to consume, we say that the instructions have retired. Okay, that means that they have done their job and they can be discarded by the processor. Okay, otherwise they are still in some sense in the pipelining stage. They have to wait until the results of the previous instructions are committed before they are committed. Okay, so processors implement this. All processors implement this. There are variants, but one of the most popular algorithms to implement this notion of reordering is called Tomasulo's algorithm. Okay, so while instructions retire in program order, and while you see that the committed state of the processor is happening in order, the architectural state is consistent with what you expect to see, right? You don't see these reorderings in the architectural state, but not true for the microarchitectural state. Okay, so let me show you what the microarchitecture does when you have a program of this sort. Okay, so let's look at the simple 3-line program. Let's assume that the first line of the program is some instruction that raises an exception. Okay, it causes, maybe it's a divide by 0, it causes the hardware to fault or whatever. Okay, and so what happens is that if you were to execute this program on a real processor, the line 3, which in this case it's something called access probe array data times 4096. Okay, it doesn't matter exactly what it is, but it's a probe array, the kind of probe array that you saw when I was talking about cache covert channels. Okay, and this is a statement to go and access some particular element of this probe array that's referenced by this data. Data times 4096 is the location that you want to access, and that's a statement over there that ultimately will go and access something in the probe array. But in any real execution of the program, in any concrete execution of the program as seen by the programmer, that statement should never execute. Why? Because in program order, if you look at execution in straight line order, that raise exception is executed and the program just stops. It has to terminate so that access is never reached. Okay, but not so within the microarchitecture. When you have out of order execution, when you have speculative execution and so on, the processor can execute statements out of order. There is no data dependence between line 1 and line 3, right? So line 3, the processor feels free, the pipelining stage will feel free to go and execute 3 and then store the results speculatively in microarchitectural state, okay, without committing them to the hardware, okay? But when it actually executes instruction 1, it will see, okay, there's an exception, I have to abort the program, and it discards all of that microarchitectural state. Okay, so it is like, when you are, you write, an exam, and the thing that you commit in the exam is basically what you write in the answer sheet that you submit to your at the end of the exam. On the side, you may have sheets where you do rough work, okay, and you throw them or you discard them at the end of the exam. But what if at the end of the exam, so you're allowed to make mistakes in rough work, right? If at the end of the exam, in addition to your answer paper, if the instructor says, I want to see your rough work and I'm going to cut points based upon what you did wrong in the rough work, how would you feel, right? That's exactly what's going on, okay? So over here, the rough work done by the processor in some sense, right? It's doing rough work, and all that rough work is thrown when the raise exception statement is executed. But unfortunately, because of out-of-order execution, the effects of this access statement may be visible in microarchitectural state. In other words, if you were to go and probe the cache, for example, this particular element, data may be some variable that was initialized earlier in the program, right? I'm just showing you a snippet. Maybe data is like 1, okay? Then if you go and access the first element of the array, the time to access the first element of the array will be lesser, okay? So you will see this in the microarchitectural state, okay? This exact effect that I showed you will appear in microarchitectural state. Okay, so let's see. Now I'm going to tell you, we have covered everything that we need for Meltdown, so let me actually tell you about Meltdown. So what is, yeah? No, the cache is not the, so you're confusing two aspects of execution. The TLB is a cache that's used to store virtual to physical mappings, okay? So most real caches are virtually indexed, physically tagged, VIPT caches, okay? So in which case you have another process can actually go and access the same cache line, and it will see this the effects over here. In particular, if the processes are related using a parent-child relationship, it's possible to go and access, which is what I'm getting to next, okay? So most real caches are what are called VIPT, virtually indexed, physically tagged. Okay, so let me tell you, this is the same slide. Okay, so Meltdown, here's a setup, okay? What we want to do is that, as I told you earlier in the talk, there is an invariant. The invariant is that no userland process is supposed to go and read any location of memory in the kernel, okay? So the kernel memory is supposed to be isolated from the userland. If the process ever tries to manufacture a pointer that references a location of the kernel and dereference it, immediately the processor will throw an error, okay? It's an exception. It's sort of baked into the silicon, the logic of the processor. So what we'll do is we'll break that invariant. We are going to allow userland code to go and access kernel memory, okay? And the way we will do it is using speculative execution. So here is the way that it works, and here's our setup. There are going to be two processes that are going to have a parent-child relationship. So a parent process gets started on the machine, and this parent process will fork a child process. And the child process, this is the child process, this is the parent process, okay? And they're going to communicate with each other. This is Alice, that is Bob, in some sense, okay? Now, what the child process is going to do is that it is going to go and read some data from the kernel memory, okay, speculatively, okay? So when it actually tries to go and read that location in kernel memory, so if you're going to write some piece of code, that piece of code is going to be called what is called transient instructions, okay? So this is an instruction sequence that should never execute in any real world execution. It always crashes, okay? So in other words, if I execute that instruction sequence and I see the effects on the process will always crash, okay? But it changes the microarchitectural state of the processor. It changes the way that the cache lines are set up. So the child process is set up with these transient instructions whose sole purpose is to go and try to read a secret, which will cause the child process to crash, okay? But the hope is that these instructions are executed speculatively so that when the crash happens and when the child process is killed off, the microarchitectural state has changed. And the goal for this parent process will be to try to go and probe that microarchitectural state and make that state explicit, okay? So that it can read the secret. Okay, so the secret is going to be, for example, some location in the kernel memory that stores, let's say, a particular virtual to physical mapping or some cryptographic key or whatever, right? It's a particular address in the kernel whose value you're interested in, and the fork child process will try to speculatively read it, but it's going to die. It's going to die 100% of the cases. It's going to die. It's never going to succeed in real world execution, but it will change the microarchitectural state. So let's see how this will work. Okay, so this is the full attack sequence. This 5 instructions is the full attack sequence for Meltdown. And even in this 5 instruction sequence, just 3 instructions are important. The other 2 are for to make the code more robust. So this transient instruction sequence is this 5 instruction sequence. The first 2 are comments, 3, 4, 5, 6, 7. Okay, and what we'll do in the next few slides is that we'll walk line by line over these instructions and then see how this is going to happen. The attack is going to happen. So all we will assume is that RCX, which is a machine register, is initialized with the kernel address whose contents you want to read. Okay, there is some kernel address that you know contains some secret you're not supposed to read, but you know the address of that location, and you're going to initialize RCX with that, with the address of that kernel location, and you're going to create a probe array in memory, just like before. You are the attacker, you are the parent, you created this probe array, and RBX is going to contain the address, the initial address of that probe array, the beginning, the first element of that probe array. Okay. With that said, let's look at the attack. Okay, and we are even going to ignore the retry now. It's just a loop, right? The attack actually works as a loop. Line 3 is retry, and you will see that line 6 is a loop back to retry. Okay, so we will focus on line 4 and line 5 now and see, because that implements the core of the attack. The core of the attack in this case is to read that one location in memory. Okay, and you can imagine if you can read one location properly, you can write another outer loop and then iterate through all of the locations in memory and then produce a complete dump of kernel memory. Okay, so that's what we are going to do. The attacker wants to learn the value of a particular byte that is stored at this particular kernel memory address, that is, and the value of this address is stored in the RCX register. So what I'll do, the child process is going to do this, that it's going to read the secret. Okay, what it's going to do is that it's just saying, look, move the lower bytes of this RCX into this register AL. Okay, so this is nothing but it's reading the least significant bits of this RCX into RAX, and essentially RAX. So AL is the least significant bytes of this of RAX. If you look at the Intel x86 instruction, the Intel programming manual is this thick. Okay, and it's this thick because there are many ways to reference registers. You can reference a register as RAX, but you can also talk about the least significant byte of that same register using AL. Okay, so even though RAX is one register that contains 4 bytes, AL refers to the least significant byte of that register. It's just what Intel gives you. Okay, so this instruction should cause an exception if it's executing userland. Okay, why? Because it's going to try to dereference that particular location RCX, which is sitting in the kernel. So if any real program tries to execute this, immediately the hardware must throw an exception saying, hey, userland trying to access kernel land, not allowed. Okay, but the problem is that due to out-of-order execution, subsequent instructions may already be executed speculatively. Okay, so the exception is going to be handled only when this line 4 is going to be retired, when its effects are going to be committed. But until then, it's free to execute speculatively. But the problem is that in doing so, the microarchitectural state, the cache state may have changed. Okay, so what happens over here? Well, what's happening here is that this value of RAX, you're shifting it left by 0xc, which is 12. And that's equivalent to multiplying that same number by 4096, 2 power 12. Okay, bit operations. Okay, and so what you're going to do is that you're going to use this location RAX, the value in RAX, to index into this probe array. This probe array is set up so that every page of every element of this probe array is 4096 bytes long. Why 4096? What is special about 4096? No, cache lines are typically 64 bytes long. 4096 is the size of a page in the kernel. Okay, so it's going to multiply that by 4096, and essentially what's going to happen is that this RAX is going to be used as the index into the probe array, and that happens in line 7. Okay, so essentially what it's doing is that it's reading the value in RBX plus RAX, right? RBX is the first element plus RAX, which is the index, and it's just going to read it. Okay, so the probe array is of size 256 times 4K bytes. Why 256? Then you're trying to read 1 byte of value. What's the size of the element that you're trying to read is 1 byte long. AL, right? You loaded everything into AL, right? You moved a single byte into AL. Now, how many bytes are there? There are 256 bytes. So if you want to go and identify which byte it was, you better have a probe array that loops over all the possible bytes. That's 256. So a probe array is 256 times 4K bytes long. And all you need to do is to go and reference that particular element in the probe array. that is immediately stored into the cache, right? That happens on line 7. Okay, so line 7 moves the corresponding entry from the probe array into the cache, and what at this point happens is that the cache will have been loaded with the element with the corresponding contents of probe array of x in this case, where x is nothing but the value of that location multiplied by 4096. Now the parent process can do exactly what Alice did, which is to probe which is to sequentially loop through all the elements of the probe array and figure out which element of the probe array had a lesser access time, okay, and it will know the value of x. That's it, okay. So that's to learn the value of x. If you want to iterate through all of the elements of the kernel, you have an outer loop where you iterate through all of the addresses of the kernel and dump them out using this inner loop. Okay, and that's how the attack works. Okay. Okay, so what is the goal of line 3 and line 6? Well, believe it or not, attackers also like to make their code robust and resilient and crash proof. Okay, it's not just the good guys. Attackers also want to do this. So the role of line 3 and line 6 is to make the code more robust, is to make the attack work in more cases. Okay, and it is to deal with what are called race conditions. So what is the race condition here? You're all familiar with race conditions when you write software, right? If you don't use synchronization properly, you try to read the value, another one is trying to write the value, and all of a sudden you have non-determinism in your execution. So here the non-determinism is that the attacker is trying to race against the hardware. Okay, the hardware is trying to commit the state that it's executed speculatively as soon as possible by taking all of the instructions that executed out of order, committing them, and then getting to the instructions that need to be committed, and then move on. Okay, but the attacker is trying to leverage the fact that instructions executed out of order. So the attacker is in a race with the hardware. He needs to go and read the microarchitectural state before the parent process crashes, because the instruction that tried to access kernel memory is going to cause the child process to crash. Okay, so he's playing a game with the hardware, and there's no guarantee he will succeed all of the time. But the idea is that you would like to get the microarchitectural state committed into the parent process in as many cases as possible. Okay, so in some machines the exception is not handled and the process crashes. But what happens is that the processor, it zeroes out the registers before it crashes. Okay, so what it's doing over here is that if the zeroing out happens faster than this operation on line 5, this shift right, the attacker will read the wrong value for this x. Okay, so what this is doing is that it's trying to execute this 4 and 5 many times if it sees a 0 value for this register. Okay, so a 0 means that the processor tried to zero out the registers before just crashing the code, and you're playing a race here. If the code crashes, nothing executes. But if you had the chance to read the register just before the code crashed, you would still see a 0. Okay, you want to avoid those error cases, so it's called zero noise bias. Okay, as many times as possible, if I see a 0, I'm going to skip over. If it is in fact a 0, well, then I will see 0 all of the time, and I can assume it's a 0. Okay, so what's the application of this attack? Well, I can produce a complete memory dump of a machine. Okay, which is that I can go. Remember, the page table of every process is loaded into the kernel memory. So if I go and access an arbitrary location of the kernel memory, that location could be a page table. And then I can go and iterate through all of the locations in memory and dump out the private contents of every process that's running on the system. Okay, which means that if I have another attack process, I can go and dump out the contents of your browser window, and your browser window and your running browser process has all of your saved passwords if you choose to save passwords, and the attacker learns all of your passwords. Okay, so I'm going to show that. So you can obtain a complete memory dump. Okay, and this is an example of a memory dump that was produced using Meltdown. And you can see from this memory dump, there are tools to actually go and make sense of this memory dump. One of the most popular tools is called Volatility. It's an open source tool. You can actually go and see, this is a tool that read from this memory dump. And you can see over here that it was able to reconstruct the saved logins of a browser that was executing at the time that the attack happened. So you can see, for example, and here, www.amazon.com. Here's the username for that account over there, and here's the password. Okay, a complete dump of the memory of the system, and this was against Firefox running on an Ubuntu system. Okay, so this is Meltdown. Fortunately, there is a defense against meltdown. And what's the defense? Well, so today, as I was saying, the kernel is loaded into every processor's virtual address space. The defense against meltdown essentially creates two process virtual address spaces for every process. One, which you see when you are in the kernel mode of the processor, where the entire kernel is loaded into the process address space. Okay, and another that the user space sees when it's in the user mode of execution. So there is no way that if you're in this mode of execution, you can go and reference an address in the kernel address space, because that address won't even make sense. It's not even mapped into your process. So the kernel, only a portion of the kernel is mapped into your process address space. The portion that contains, for example, the stubs that implement your system calls and so on. The rest is not even mapped there. But this doesn't come free, okay? There is a significant performance penalty if you implement this defense on the order of around 30%, okay? And nobody is willing to accept that kind of performance penalty. So there is a trade-off, okay? So this is Meltdown. I am out of time, so I will not talk about Spectre. Yeah. So Linus calls everything garbage, okay? So, but I'm just telling you the kind of reaction that has been elicited. We can't go by what he is saying, right? The point is that if you were to take a scientific perspective, there is a performance penalty, because what happens is that every time, so how do you switch between two different address spaces? What happens is that the processor, there is a special register that holds the root of the page table, okay, the page table root register. That has to change. Every time that changes, there is an associated cost, which is that TLBs have to be flushed, possibly even cache state has to be flushed. Every time you switch between two processes, all of those things happen, which means that the TLB has to be repopulated, the caches have to be repopulated. That's the performance cost, right? So, and there is no way around it, right? Because TLBs cannot not be flushed unless you have a new design for the TLB with indexing for which process entry is stored. So that's the reason for the performance penalty. Now the reason that he called it this is because these attacks, these defenses were developed in a hurry that caused instability. It's incredibly hard to go and write low-level code that deals with the page table, because now you're in a part of software that is actually dealing with hardware-specified contracts. The format of the page table, the format of how you access the page table and so on are actually specified in the Intel manual, and your software better conform to that, right? If there is any small bug, it's going to cause operating system level instability, which means the whole machine is going to come crashing down. That's why. When you develop things in a hurry, there are going to be crashes if you don't consider corner cases. That's why he called it this. But in any case, this is not really an elegant fix. It's just a fix that exists. Yeah. I don't see any loss. What option do you have? It's not like you're not going to buy processors. You're going to continue to buy them, right? So my colleague who works in architecture, who you heard from yesterday, Arka, he worked in AMD, and he proudly says AMD was free from this bug. The reason, can you guess the reason? Why was Intel's processor free from the bug that AMD's processor free from the bug that Intel, but Intel what? So ISA is exactly the same. They both implement the x86 ISA. It crashes when it sees this instruction. That's why, right? So it's about the time when you decide to throw the exception. During execution speculatively or during retire. From a programmer's perspective, they are both the same, because you're not supposed to see into the microarchitectural state. That's hidden away by abstraction. But that abstraction was what this breaks, and AMD, for whatever reason, decided to crash in their speculative state. So AMD was protected against this. But they were not protected against Spectre. Okay? Spectre, we don't know about Spectre. You want to know about Spectre, but you will not get tea then. You are saying it's fine, the others will come and beat me. Or they'll beat you. That's fine by me. So, okay. I'll tell you quickly about Spectre, right? In fact, Meltdown is a very easy attack to explain. Spectre and Meltdown can be exploited on, you can launch Meltdown on any machine, okay? Standalone machine, which means that there does not have to be a vulnerable program that acts as the host in some sense for the attack. It's a standalone attack, as you saw here, right? There is nothing here. I did not exploit a vulnerability in a browser. I did not exploit anything. No vulnerabilities in Flash Player, nothing, right? I just wrote a program that spawned a child process and then did this, right? In contrast, Spectre requires a host program. So it's much harder to launch than Meltdown. At the same time, there is no defense that's known for it, okay? That's what has been the saving grace so far, which means that even though there's no defense, it's also much harder from the attacker's perspective to launch something like Spectre. So Spectre affects everything, okay? Intel, ARM, AMD, everything. And the other form of execution, that speculative execution that it exploited, you can see from the logo, it exploited branch prediction. Okay, that's why this guy is holding the branch. And it's harder to deploy, right? And there is no known defense to date. So the idea here is that it exploits branch prediction. So what is branch prediction? So every piece of hardware implements something called a branch predictor. For a while, you know, this was the hardware industry's solution to Moore's law. What's Moore's law, right? The processor, the number of transistors double every 18 months, right? And they didn't know how to use these transistors. So today they know how to use it. They just implement multi-cores. But they didn't know for a while how to use it, and they put all those extra transistors to use by implementing branch prediction logic. In fact, the earliest, to my recollection, the earliest known application of so-called what is deep learning these days was for branch prediction, because all processors use what is called neural branch predictors now. They use some simple form of neural nets to do branch prediction. Okay, and here the idea is that the hardware is predicting the likely outcome of a branch based upon past history. You know, if a branch executed, true 5 times out of 10, it's hard to predict. But if they executed true 9 times out of 10, chances are that the 11th time also is going to be true. So you can execute it speculatively, assuming that it's true. If it turns out to be false, fine. We'll throw away its speculative state and then execute concretely. So the idea is that most of the time you'll see a speed up. Sometimes you'll just see the regular execution, right? So in a speculative execution, for example, over here, you see the store, load, compare, and then there is a jump on 0, right, on some register. So you can either take the true branch, or in this case, or the false branch, and the hardware at this point decides, okay, you know, it's going to, the concrete execution may still be at the store, but then the hardware races along doing speculative execution. It reaches this jump on 0, and then it decides, okay, you know, I've seen this branch being true most of the time. Let me continue to execute along the true branch. Okay, so in this Spectre, you need a host program, as I was saying, which is a victim program that has some sort of a vulnerability, and you need to find an instruction sequence that contains a branch. Okay, so what we'll do is that we will, in preparation for this attack, we will, the attacker will have to force the program to execute in such a way that that the hardware's branch predictor is trained to true for this particular branch that the attacker has identified. Okay, so he identifies some if statement in the program, and he executes the program multiple times so that, you know, it goes true most of the time. Okay, and then the attack is that you're going to feed it a malicious input that would cause the branch to go in the other direction. So what happens in this case is that, you know, the hardware has speculated, all of that state, it's accumulated, it's going to have to throw away, right? But what's going to happen is that as it executes speculatively, the hardware is going to assume that the true branch will be executed, and it executes all of those speculatively, affecting the microarchitectural state. What ultimately happens is that the false branch will be taken in a concrete execution. Okay, so you use a speculatively executed true branch to extract data from the victim program. Okay, so my description here is also going to be much less precise than the Meltdown attack, because the attack is also much harder to explain. But here is roughly how it works, right? So supposing you have this program pattern in this vulnerable program, x less than array 1 size, y equal to array 2 of array 1 of x times 256. Okay, so this, in some sense, this array 2 is this probe array. Okay, and array 1 is the unsigned byte array of size array 1 size. Okay, and suppose, you know, x is the value of that's derived from the program input. So it can cause the program to go either the true branch or the false branch. The attacker can basically control whether the branch goes true or false based upon the value of x. So what we are going to try to do over here is we are going to try to do an array bound out of bounds. This is typically not allowed, right? So it's checking over here in the program, it's checking that X is within the array bounds of array 1. Okay, it's checking only if X is less than array 1 size, am I allowed to go and access that memory location. Okay. So in any real execution, if X was greater than array 1 size, you would never see that execution because the branch will be false and then it will never execute. But what we are going to do is that we are going to assume that the attacker provides a value of X that's greater than array 1 size, and speculatively the hardware is going to do an array bound out of bounds. Okay, and we are going to use that for the attack. So in this program, maybe there is some secret data S that is beyond the bounds of this array 1, okay, that you want to access, and you're going to use this array out of bounds to go and access that location. Okay, okay. So here is the attack, right? So your array 1 size, this is your array 1, and at some location in memory is your secret S that you want to read, and you know exactly where it's in memory, right? So it's some distance away from the beginning of the array, and you feed the value of this X so that it is equal to this, right? In any real execution, it is never going to work, but speculatively, because of the branch prediction, because the branch predictor is trained to go in the true branch, it will just go and execute y equal to array 2 of array 1 of this times 256. It just goes and does it, right? It's all speculative state. Okay, so the attack preparation, as I was telling you, is to execute the program long enough, the number of values of X, so that the predictor is trained to take the true branch. And you arrange for the cache to not contain this array 2 and array 1 size, okay? So that if you were to try to access array 2 and array 1 size, these two variables, it takes longer for the hardware to load them from memory, okay? The reason you want them to take longer is because now you're going to have to try to win a race with the hardware, and as the hardware is fetching these things from memory, you have finished your attack and you're out of the way, okay? So you arrange for the cache to contain this secret value S, okay? So how can you do that? Well, think about S as being a cryptographic key, okay? If S is a cryptographic key, maybe you can encrypt some values using S, so you know S is in the cache, right? You do not have to know the value of S. You can just ask for the program to encrypt it. So, the program will load S and that S will be in the cache, right? That's why, like I'm sweeping a lot of things under the carpet. How do we arrange for S? It depends a lot on the victim program, right? If it is a program that does encryption and this S is a key, then it will be in the cache. But how you arrange for this S to be in the cache depends a lot on the specific victim program that you're attacking. This is why Spectre is a much harder attack to design than Meltdown, but it's still possible. Okay, so now the actual Spectre attack is that you execute the program with X equal to this. So what's going to happen is that this X less than array 1 size will lead to a cache miss, okay, because array 1 size is not loaded into the cache, okay. What this does is that it leads to a delay in fetching this array 1 size, and by the time that the processor is actually going to fetch array 1 size and compute X less than array 1 size and so on and figure out the result, speculatively it would have done things, but by the time it figures out the concrete execution, the attacker will basically go and speculatively read the speculative branch would have executed array 1 of this, which will lead to a hit in the cache for this S. Now all you do is that this code will then go and proceed to read this array 2 of S times 256, just that line over there, okay? And this will be a miss in the cache, okay, because array 2 was not loaded in the cache. This was our setup, right? Now array 1 size might have arrived by then, and then processor realizes that there was a mistake in the speculation, okay, that I took the true branch instead of the false branch, but the speculative read has already affected the cache state, and lo and behold, exactly like in before, the parent process can go and read everything from the cache state and done, right? You know the value of S. Okay, so let me move forward, right? What was Spectre used for? So it was used to break out of sandboxes. Okay, so what's a sandbox? A sandbox is basically a safe region for code to execute, right? So every browser implements a sandbox, for example, for JavaScript. You've all executed JavaScript. When you go and read your Gmail, you're basically executing JavaScript. When you see maps, you're executing JavaScript. So how is it that the JavaScript that is sent to you on your browser by Google, how is it that Amazon has a ton of JavaScript code? You might or might not know this, but every time you hover a mouse on top of a product, there is JavaScript code executing that tells Amazon how much time you spent your mouse hovering over that particular product, so that next time they can give you more relevant ads, okay? At some point it used to be that. So you spend more time over a product, chances are that you're interested, they will send you ads for that. Right? So how is it that the code from that the JavaScript code that's sent to your browser from Amazon is isolated from the JavaScript code that is sent by Google, right? Google clearly should not be able to read your Amazon JavaScript code and the state that it processes, and vice versa. So the way that this is done is that the browser implements a sandbox for JavaScript. Every piece of JavaScript code executes in the sandbox, and it cannot escape the sandbox. Okay, so what Spectre was used to do was that it was used to step out of the bounds of the sandbox. The sandbox is nothing but, you can think about it as a region in memory that you should never escape. And Spectre, as I showed, you can step out of the bounds of an array. Okay? So this was used to break out of the sandbox and therefore access arbitrary browser memory. So what this means is that now Google can read your passwords that are saved in your password manager, right? Well, if you attack Google code, right? But that's the idea. You break out of the sandbox and then you go and read arbitrary program state that you're not otherwise allowed to read. And so that was the application of Spectre, and with that, that's the end of my talk.